There's something about symmetry, right? It just feels right. Like it's elegant, like the universe is this tidy, well-organized thing.
Yeah.
But then what happens when it's not? What happens when things get a little messy, a little less predictable?
Right.
That's what we're going to look at today with a little help from the one and only Richard Feynman and his lecture on symmetry in physical laws.
Oh, Feynman, he's brilliant. Always makes you think.
Absolutely. And even if you think you've got a handle on this symmetry business, trust me, Feynman will find a way to turn it on its head. You ready to dive in?
Absolutely, let's do it. I always love hearing how Feynman explains things. It's never what you'd expect.
So, to kick things off, how about we start with the basics? What does it even mean for something to be symmetrical?
Well, I think we all have a sort of intuitive sense of it, right? Like, think about a vase. You can turn it, spin it around.
And it still looks the same from different angles.
Exactly. That's symmetry in a nutshell. It's about balance, about things looking the same, even when you change your perspective.
But Feynman, he doesn't just stop at vases and shapes, does he? He takes this idea of symmetry and applies it to the laws of physics, to the very fabric of the universe.
And that's where it gets really interesting, because we're not just talking about how things look anymore. We're talking about how they behave,
Yeah.
the rules that govern everything around us.
It's like he's saying the universe has its own set of rules, its own kind of symmetry. And these rules, well, they should apply everywhere and every when.
Exactly. Like, if you do an experiment here on Earth, you'd expect to get the same results if you did that same experiment on Mars.
Right.
Or even a million light years away.
Right. The laws of physics shouldn't be dependent on where you are in the universe.
Precisely. And it's not just about location, it's also about time.
So whether you started an experiment today or 1,000 years ago, the same laws should apply.
Exactly. Feynman uses this really interesting example talking about buying General Motors stock. He suggests the laws governing the stock market, well, they should be timeless, at least in theory.
It's classic Feynman, using these everyday examples to illustrate these really profound ideas. But then he throws in this other example about swapping out atoms in an experiment.
Oh, right, like all electrons are fundamentally the same, so you should be able to just swap them out without changing the outcome.
Yeah, like they're these tiny little Lego blocks that make up everything, and it shouldn't matter which specific block is where, as long as they're all in the right place, right?
It's a mind-boggling concept when you really think about it, but it speaks to this deeper idea that there's a fundamental blueprint to the universe, a set of rules that holds true no matter what.
And this ties into some pretty big concepts in physics, right? Like conservation of energy and momentum.
Absolutely. These are cornerstones of our understanding of how the universe works.
Okay, so for those of us who haven't brushed up on our physics lately, could you unpack those a bit? What exactly do we mean by conservation of energy and conservation of momentum?
Sure. So conservation of energy, simply put, is the idea that energy can't be created or destroyed, only transformed from one form to another. Like when you roll a ball up a hill, its kinetic energy, the energy of motion, is converted into potential energy, the energy of position. And then as it rolls back down, that potential energy is converted back into kinetic energy.
So it's like the total amount of energy in the system always stays the same, it just changes form.
Exactly. Now, momentum, that's a bit different. It's basically a measure of an object's tendency to stay in motion. The more massive an object is and the faster it's moving, the harder it is to stop.
Okay, and this ties back to symmetry.
Exactly. It all comes back to this idea of translational symmetry, which basically means the laws of physics are the same no matter where you are in space. So you can move that ball to a different room, a different country, even a different planet, and those same laws of motion, those same principles of energy and momentum conservation will still apply.
So the universe has this underlying consistency, this beautiful kind of order, even in the midst of all this seeming chaos.
That's the beauty of it. But of course, as with all things Feynman, just when you think you've got a handle on things, he throws in a curveball, right? He starts poking holes in this idea of perfect symmetry.
Because nothing's ever quite as simple as it seems, is it?
Not with Feynman. He shows us that while symmetry might be the rule, there are some fascinating exceptions. Some places where those seemingly unbreakable rules start to bend or maybe even break. And that's where things get really interesting.
Okay, now you've really got me hooked. Where do these cracks in the mirrors start to show? What makes Feynman question this seemingly perfect symmetry?
Well, one of the most striking examples he gives is this idea of scaling.
Scaling, like zooming in or out on something.
Exactly. He uses this really vivid example of a cathedral made of matchsticks. Imagine you built this beautiful, intricate cathedral, perfectly symmetrical, out of thousands of tiny matchsticks.
Okay, I can picture that. A miniature masterpiece.
Right. But now, imagine trying to build that same cathedral, but on a much larger scale, using matchsticks the size of telephone poles.
I have a feeling it wouldn't be quite as structurally sound.
Not at all. It would crumble under its own weight. And that's because the laws of physics operate differently on different scales.
So something that might be perfectly symmetrical and stable at a small scale can completely fall apart when you try to make it bigger.
Exactly. And Feynman links this back to Galileo, who centuries ago was already grappling with this idea. It's fascinating to see how these fundamental concepts have fascinated thinkers for so long.
It makes you wonder what other things we take for granted, what other seemingly obvious symmetries might not be so straightforward when we look a little closer.
That's the beauty of Feynman. He makes you question everything. And that's precisely what he does when he starts talking about time reversal. This is where things get really interesting, right? The idea of time running backward. It's like something out of a science fiction movie.
Right. Everyone wants to hop in a time machine and go back and fix something or relive a moment. But we're talking about something much deeper here, right? We're
Right.
talking about the laws of physics themselves.
Exactly. We're asking if we could somehow hit rewind on the universe, would those fundamental laws still hold true? Would everything work the same way, just in reverse?
So like instead of watching an egg break, we'd see it unbreak, all those tiny pieces coming back together.
Exactly. Now, obviously, on a large scale, that seems impossible, right? You can't unspill milk or put Humpty Dumpty back together again. But Feynman asks us to consider, what if we zoomed in to the tiniest level, to the realm of individual atoms?
So we're talking about seeing the universe like a billion times smaller than an ant, right? To actually see the individual building blocks of matter.
Yeah, something like that. Because Feynman argues that at that level, time reversal might not be so outlandish. If you could somehow track the movement of every single atom involved in, say, an egg breaking, and then reverse their motions precisely, the laws of physics wouldn't necessarily object.
Wait, are you saying that if we had some kind of supercomputer that could keep track of every single atom, we could theoretically reverse time, at least on a small scale?
That's the implication, isn't it? We think of time as this one-way street, always moving forward. But at the atomic level, it might be more like a highway with traffic flowing in both directions.
That is seriously mind-blowing. So the arrow of time might just be an illusion.
An illusion created by our limited perspective of the universe. We see time moving forward because we only see the macro consequences of trillions of tiny interactions, not the interactions themselves.
Okay, so that's time reversal. But what about something like rotation? If you spun an experiment around, wouldn't that definitely change the outcome?
You'd think so, right? It seems totally intuitive that spinning something would make a difference.
Yeah, like imagine a merry-go-round. You spin it slowly, it's one thing. Spin it really fast, well, people are going to start flying off.
Exactly. And this is where Feynman really starts to push us to think critically about what seems like common sense. It turns out rotation, while a seemingly simple symmetry, reveals another layer of complexity in the universe.
Okay, I'm intrigued. Why is rotation different from, say, moving an experiment to a different location?
Because with rotation, you're introducing a new force into the equation, centrifugal force.
Ah, right. The force that makes you feel like you're being pulled outward when you go around a sharp curve.
Exactly. That force isn't present when you just move an experiment from one place to another, or even when you reverse time at the atomic level. It's a direct result of the spinning motion.
So, unlike those other symmetries we talked about, rotation introduces a new factor, a new force that can influence the outcome of an experiment. It's not just a matter of perspective anymore.
Precisely. And this leads us to one of the most fascinating aspects of Feynman's lecture. This deep connection between symmetry in the laws of physics and what are called conservation laws in the quantum realm.
Okay, whoa. Hold on a second. We're already dealing with time reversal and microscopic egg reconstruction. Now we're going quantum.
Don't worry, it's not as complicated as it sounds. Think of it this way. Each of these symmetries we've been talking about, translation in space, translation in time, rotation, they each correspond to specific conservation laws in the quantum world.
Okay, I'm listening. Tell me more about this connection.
So let's take translational symmetry, the idea that the laws of physics are the same everywhere in space. This symmetry is directly related to the conservation of momentum.
Okay, so the fact that we can move through space without the universe suddenly changing its rules is directly related to this idea of momentum being conserved.
Exactly. And it gets even more mind-blowing. Translation in time. The idea that the laws of physics are consistent over time is directly related to the conservation of energy. Energy can't be created or destroyed, only transformed, and this principle is fundamentally intertwined with the time-independent nature of the laws of physics.
Okay, I think I'm starting to wrap my head around this. It's like these symmetries are the bedrock upon which these fundamental conservation laws are built.
Exactly. And to round things out, rotational symmetry, our spinning experiment, is tied to the conservation of angular momentum. This dictates how things spin, how they maintain their orientation, and how that rotation is affected by external forces.
So even in the often confusing world of quantum mechanics, these fundamental symmetries hold a key to understanding the underlying order of the universe.
Precisely. And this connection between symmetry and conservation laws is one of the most profound and beautiful aspects of physics. But just when you think you've got a handle on things, Feynman throws us another curveball: the mystery of reflection.
Reflection, that seems pretty straightforward, right?
Yeah.
Like looking in a mirror. If the laws of physics are the same everywhere, they should be the same in a mirror image, right?
Boop, that's what you'd think, right? Like, a mirror image should just be a flipped version of the same thing. But Feynman, he has a knack for finding the wrinkles in these seemingly simple ideas.
So where does this whole mirror image thing start to get complicated?
Well, he uses this great analogy to illustrate the problem. Imagine trying to explain the difference between left and right to an alien, but you can only talk to them over the phone.
Okay, so no visual aids, no pointing, no gestures, just words.
Exactly. And you can't assume they have any of the same cultural references, right? You can't be like, imagine a lefty baseball glove.
Right. It's like trying to explain the color blue to someone who's been blind since birth.
Exactly. You have to find a way to describe it using only fundamental concepts, basic laws of nature. And for a long time, physicists believed it was impossible to distinguish between left and right using just those basic laws. They thought these concepts were just matters of perspective, like up and down.
But Feynman wasn't convinced.
Not quite. And this is where we get into one of the most fascinating chapters in the history of physics. It starts with these tiny particles called tau and theta mesons.
Okay, I'm going to be honest, I'm not super up on my particle physics. What are these mesons you speak of?
Think of them like really, really, really tiny subatomic particles. And what makes these particular mesons so interesting is that they're basically identical in every way except for how they decay, how they break down into other particles. And according to the prevailing theories at the time, this difference in decay, it shouldn't have been possible if left and right were truly interchangeable at a fundamental level.
So these little particles were breaking the rules.
They were throwing a wrench in the whole system. And it caused a major shakeup in the physics world. So this brilliant physicist, Chan Sheng-Wu, she designed an experiment to get to the bottom of this.
An experiment involving mesons.
Well, she actually used a different element, cobalt-60, which is radioactive. She cooled it down to super low temperatures and a strong magnetic field, which caused the cobalt atoms to align themselves, kind of like tiny compass needles, all pointing in the same direction.
Okay, so far so good. And then what happened?
Here's where it gets interesting. Wu observed that the electrons emitted during the cobalt-60 decay, they weren't flying off randomly in all directions like you might expect. They actually showed a preference for a particular direction, a specific handedness relative to the magnetic field.
So the experiment itself had a left or right bias, even though in theory it shouldn't have mattered.
Exactly. And that was the groundbreaking discovery. It provided the first undeniable proof that a fundamental force of nature, the weak force, actually violates this mirror symmetry, this parity as it's called, at a fundamental level.
Whoa. So the seemingly simple question, can you define left and right using only physics, led to the discovery that one of the fundamental forces of the universe doesn't play by the same rules in the mirror.
Exactly. And it challenged our understanding of matter and antimatter as well.
Wait, what? How does that fit in? I thought matter and antimatter were just like mirror images of each other, just with opposite charges.
That's what physicists thought for a long time. But this whole parity violation thing threw a wrench in that idea too, because it turns out that because of this violation, right-handed matter, that is, matter spinning a certain way relative to its direction, actually behaves more like left-handed antimatter.
Okay, so this is getting seriously weird. So much for those neat and tidy mirror images. But this whole thing with the cobalt-60, that means we could actually explain left and right to our alien friend, right?
We could. We could tell them to do the same experiment, and because of this parity violation, that experiment would always give them the same handedness no matter where they are in the universe.
Wow. That is seriously cool. It's like the universe itself has a slight but fundamental preference for one hand over the other.
Yeah.
But why? Why would the universe be almost perfectly symmetrical, but with these tiny yet crucial exceptions?
That's the million-dollar question, isn't it? And, Feynman, always the playful one, he offers a rather humorous suggestion.
Oh, I'm all ears.
He jokes that maybe God, in his infinite wisdom, made the universe almost perfectly symmetrical just to keep us humans from getting jealous of his perfection. Had to throw in a few flaws to keep things interesting.
Classic Feynman. Always with the jokes, even when tackling the biggest mysteries of the universe. But, jokes aside, this deep dive has been incredible. We started with a simple question about symmetry, and we ended up in the strange world of particle physics, all thanks to Richard Feynman and his unique way of looking at the world.
That's the beauty of Feynman. He reminds us to never take things for granted, to always question our assumptions, and to find joy in the unexpected.
Because sometimes those cracks in the mirror, those places where our expectations break down, that's where we find the most fascinating and profound truths about the universe. So keep exploring, keep questioning, and most importantly, keep wondering. You never know what mind-bending mysteries you might uncover.